research fellow at the University of Oxford. She studied at the University of Buenos Aires and then for her PhD moved to Grenoble in France to focus on silicon photonic technologies for quantum computing. Her group in Oxford now is investigating thermodynamics for quantum devices. And just very recently, there was a PRX paper by her group about how to quantify the cost of timekeeping, which is pretty cool. So Natalia is also working on AI research, especially for quantum technology, and there especially for how to tune quantum devices better and faster than humans. And this is what she will talk about today. So Natalia, please.
Well, thank you, Mario, for such a fantastic introduction. And thank you, Florian and Leopoldo, for the invitation. So indeed, let me tell you, I'm going to share screens. I think now you should be able to see my slides. So what I want to tell you today is how to go from chips, let's say from quantum chips, to qubits faster than human experts. And this work was indeed motivated in the lab. You can see here humans, these are humans in my group, interacting with quantum hardware. And the idea is that what we do every day is we get signals coming out from our quantum hardware, we analyze them, we make decisions, we change parameters, and we send signals back to the quantum hardware, and we start the loop again. And well, this is a complex task, and it gets more and more complex the more complex the circuits get. And as quantum circuits in ion traps, semiconductor chips, superconducting chips get more and more complex, this task really becomes untractable for humans. And this is where we need, indeed, robot scientists, okay? And actually, so far, there have been, we have been trying to, as a community, to say organize all these tasks and decision making. There have been some interesting work in acyclic graphs for superconducting qubits. But now what I want to show you is what machine learning can do for these tasks. And I'm going to show you where we got so far on this endeavor. So in particular, I'm going to focus on semiconductor chips, but most of what I'm going to say is actually applicable to superconducting qubits or ion traps or other quantum circuits. So as I said, we have a semiconductor chip, and we have humans that follow a sequence of steps in order to encode qubits in this chip, okay? And once we have a qubit, actually, we need to, that's not the end of the game. We still need to follow certain steps in order to optimize such a qubit. And now this task, it's complex, as I said, because of the following reasons. One is that the parameter space that we are exploring is huge. And another of the very key points is that there is big variability between devices. It's not that we can do this process with one device and then basically copy it to all the other devices that are nominally identical. And the reason is that because these are quantum sensors, basically, and they get affected by absolutely, many things. So an electron, an atom out of place, and these devices care about it. So we need a smart way to actually go through this sequence of steps in a way that we can learn from very different scenarios. And also we are working within very narrow error thresholds that have to be above 99%. And okay, this makes this task very hard. And what we have been doing so far is basically replacing the human in this process by machine learning. And this is also not an easy task. And the reason is that, well, we have small data sets. It's expensive to take data with quantum devices. Also, again, we have big variability between devices. So the algorithms that we produce, they have to be robust against this variability. Another very common problem is flat optimization landscapes. What does this mean? Well, for a lot of the parameter space, nothing actually happens. And then suddenly all the action is restricted to a very small portion of the parameter space. Also, we have to deal with noisy data, and in some cases, even hysteretic data. So this makes also the machine learning automation quite difficult in these tasks. So, well, let's go step by step here, and let me show you where we got so far. So we have, in particular, focus on semiconductor devices, and the real question is, well, what measurements do we do to get from to go from point A to point B? So, well, mainly because it's a semiconductor chip, what we have as output is the current through these devices. You can think about these devices as transistors, that they are controlled by bias and gate voltages, and the output is a current. And we have to find the right parameters in different steps until we actually are able to encode a qubit. In particular, we encode qubits in the relative alignment between two electron spins. But that's really a detail here. What we should focus on are the inputs and the outputs of these devices. And okay, which measurements do we do, and which measurements do we require, and are the same measurements a machine would require, or a machine would require completely different measurements? So for these different steps, at least humans require the following measurements typically, which are measurements of current as a function of either two gate voltages, or a bias and a gate voltage, or frequency, or frequency and time. And we can measure the current. There are other outputs we can measure, but in principle, in the first few steps to encode a qubit, this is what we do. We do a first step of super coarse tuning. So from the device being version, we go through a super coarse tuning process, then a coarse tuning and characterization process, then fine tuning. And once we have a qubit, we can focus on optimizing it. So there has been fantastic work on machine learning applied to the semiconductor device tuning. This is not an exhaustive list. It's just to give you an idea. And today, let me focus on where we are at in this process. So we have automated fully few of these steps going to qubits. And I think one of the reasons why we have managed to go this way through is because we've been versatile in the machine learning approaches that we have applied. So some of those do not have deep learning, do not use deep learning at all. Some are basically deep learning. Some are a combination of both. And today I'm not going to have time to go through every single of them in lots of detail, but I'm going to show you what we have achieved so far, mainly for step 1, step 2 in this work here, and step 3. So we could go through that. Let me remind you that all our algorithms are in GitHub in this repo here, and you're encouraged to play with these as much as you like. So let's start with the super coarse tuning. So just to give you a better idea of what we mean by super coarse tuning. So we have these transistors, and for most of the parameters of the gate voltages in this case, we have a lot of current flowing through the device. That's not very useful. Also, it's not very useful when we have absolutely no current flowing through the device. The very useful part is where in the boundary of current and no current, there we can see, you can see these features appearing here. These features mean that we are starting to see single electron transport, and therefore that we have some hope of encoding a qubit. So that's the part where the transistor actually operates. It can be encoded, a qubit can be encoded in this transistor. So those are the parts where the features we are actually interested in. And as you can see, as long as there is 2 gate voltages that do not go very far, okay, you can see these features here and you can aim there. But actually these devices are a lot more complex. Some of them have 3 gate voltages. Now the space becomes even bigger. And here what you can see is actually the boundary between current and no current. And now you have a surface. And actually, you can see here a measurement. This is a real measurement of this surface. And you can see it's a surface that that has, you know, has a very strange shape, and it's not very easy to parameterize. And of course, this surface changes from device to device, and we don't know exactly how. And now we have to find these features in the surface, which is huge. And now you can imagine that as the number of gate voltages grow, this becomes now an hypersurface in a multidimensional parameter space. And very rapidly, the time that it takes us to measure this escalates to absolute insane times. This measurement here took us about a month and a half. We did it over Christmas so that we could take the time. But now how machine learning can actually help us basically navigate this huge parameter space? Well, what we have done is give the algorithm absolutely no information, except that to start from 0 voltages in all the parameters, and start measuring the current in one direction, which is random. So here I have plotted 2 directions, sorry, so that it's easier for me to illustrate, but you can imagine this in a multidimensional space. So the algorithm starts measuring current, and now what it does is when it sees a drop of the current below a certain threshold, then the algorithm would say, okay, there might be a boundary here, so I would stop there. And I would start exploring around that particular point. And there are 2 outcomes here. Either the current is flat, in which case it's not very useful, or it sees features. And if it sees features, again, this is interesting. This is an interesting location. So what it would do with this information is start building a model of 2 things. One is where this surface that separates current from no current actually is. So you can see this line here, that it's a guess from the algorithm of where this surface might be. Now also it would make a model of how probable is to find these features. So here what you can see is yellow is high probability of finding features, and green is low probability. And these points here are the measurements that the algorithm has actually made. So, okay, now that the algorithm has a model, then things are a lot easier, because now it can choose, next time, it can choose a promising location instead of choosing completely random. And then that promising location, because we know the algorithm knows it's promising, it can spend a little bit more time taking data around that point. So what it does is a 2D plot of current as a function of 2 of these gate voltages, and actually it can identify some particular features we are looking for, in this case, these islands of current that we call bias triangles. So there are 2 points here that are in particular tricky, which is the modeling and how do we choose these points. So let me tell you a bit more about it. So for the model, we use Gaussian processes. The idea is that we have a real hypersurface. So this is the border of this pink region. And we have a prediction of the algorithm, which is in green here, with certain uncertainty, okay? And we have some evaluations, some measurements we have done, which are these points in green here. And what we want is actually take new evaluations that give the model information in order to reduce the uncertainty of how this real hypersurface looks like. Now, once we have this model, the choice of the new measurement is also an interesting task, because first, the hypersurface is not, as I said, easily parameterizable. So what we have done in order to, let's say, probe this sample, this hypersurface, as uniformly as possible, is to simulate Brownian particles in the volume inside the hypersurface, delimited by the hypersurface where there is current flowing through the device. And then there is a matter of whenever the particles hit the hypersurface, we can consider that a random sampling of this hypersurface that is done uniformly. But now there is a bit of a trade-off here, right? Because we can go choosing random points in the hypersurface, but that would not use the information of the model. And we can use the information of the model, but then we might be missing some areas that we haven't explored and that are actually better. So in terms of how promising the features are. So we have this exploration versus exploitation trade-off to take care here. So this is a quite interesting problem. We have applied it to a particular semiconductor device that you can see here. This device has 8 gate electrodes, meaning that it has an 8-dimensional parameter space to move on. And we have benchmarked our algorithm with humans. So humans are here just to benchmark the performance of the algorithm. And because humans were not always in agreement, we have found 3 humans that gave the opinion about the different outcomes of the algorithm. And we created a measure that it's called the average number of successes. So when that particular human thinks the algorithm has been successful in finding promising features. And what we found is that if our algorithm were just picking randomly from the hypersurface different locations, we would have to wait in the order of 9 hours to see success. While with our algorithm, what we can see is that in different runs, we observe much better number of successes a lot quicker. So actually, random, it's above 9 hours. Human experts, we have asked many human experts, even very confident human experts, and they all quoted more than 3 hours. And our algorithm can do it in less than 70 minutes. Now, our latest runs, you would see, I'll show you next, are in the order of our fastest runs are in the order of 10 minutes. So this has been fantastic for us to see that indeed we can take a task, a very complex task in the lab, and perform it faster than human experts. So we have created as well in our GitHub a simulation demo where the sample is simulated and you can run this algorithm and find the features. So it's a bit like a game again. So actually, talking about scientific discovery, we have realized that we've never looked at this problem like this before, because we never measured these surfaces. That's something very weird to do. We've never thought about doing that before. And we have started doing so just because we were designing this algorithm. But something that we have realized is that once that the algorithm has a model of this hypersurface, that's a very good quantity to compare the variability between devices. Because what we can do is measure or have the model of the hypersurface of one device and have the model of the hypersurface of a second device and map them. And depending on how much do we need actually to map them one into each other, we can know how different they are and where the variability lies from one device to another. So we've done this for different devices. Here you can see the matrix that maps one hypersurface into the other is 8x8 because it's an 8-dimensional hypersurface. Now you can see that well, that matrix is a bit of a mess, and this is what I was saying before, that devices are very different from each other. But something that, so this could give you a quantitative measure of how different devices are one from the other. And also something that we have done is that we know you know, in the lab that sometimes we thermal cycle a device and it's a bit of a reset. You know, we just reset the device and start again. What we have realized is that when we cool down a device, we warm it up and we cool it down again, what we are actually doing is shrinking or expanding this hypersurface, but the hypersurface doesn't change very much. And that's something that, again, we have discovered doing the mapping of these hypersurfaces. We have also shown that our algorithm is robust not only against different devices in the same material system, but many different devices in silicon, devices in germanium silicon, devices in silicon germanium. And what we have also realized is that this hypersurface actually have a really different shape in these, well, a quite different shape in all these architectures. And this can also give us information of how easy it is to find these features in different structures and how quickly we can tune them. So actually, we have seen that for silicon germanium heterostructures, one particular type of semiconductor devices, we've seen running times of 90 minutes, in silicon FinFETs 30 minutes, and germanium silicon nanowires 10 minutes. So we are about to put these results in the archive in the following next week or so. But this shows that actually, you know, a bit like in AlphaGo, we can not only these algorithms can not only play Go, but they can play chess and, you know, other games. So basically, we can see that it's robust against a very broad range of architectures and material systems. So now, okay, we managed to find these features, but still we need to characterize them. We have worked in efficient measurements before. You can, I refer you to this paper here, but I won't have time to show it to you today. I would focus on this particular work here in which we are trying to find, once we are in the area, some very particular features. So let me show you what I mean. So the previous algorithm leaves us with some region of the parameter space where we have these particular features we are looking for, but still there is a pretty big window in which we still need to find these islands, and we would like to do so without having to measure the entire space in this window, because these measurements can be very slow. So the problem here is, as you can see, depending on where you're coming from in this parameter space, sometimes you have no information at all. For example, if you start here, you don't really know where to go because there is no features that tell you where to go. So for this, we have used deep reinforcement learning, which again, it was used for games, and Hans has talked a bit about this, so I will not go, I will not try to explain that more. But the idea is that we train an agent to find these particular features. So what we have done is divide this space in blocks, and we have left an agent that can take that can make the decision of measuring the block above, below, to the right, to the left, or in diagonal. And it has to find, the reward is to find those particular islands. And as you can see here, our agent goes directly and finds the islands. And it knows where to go because it has been trained in different measurements of different devices. So I can tell you a bit how, well, maybe I should hurry up actually, right? I have, I think I've been slower than I thought.
Yes, I think you have 15 more minutes, but we should take time
Okay.
for questions. So
Okay.
maybe 5 or 10 minutes.
Perfect. Thank you very much. So I would just flash these. This is how the algorithm works, and I would be happy to tell you more about it in the questions. But let me show you that what we see is that wherever we start this agent, it goes very quickly to these islands, and it does it much faster than it would be to actually perform the entire measurement, and even that are random agents. So if we have an agent that can choose randomly to go up, down, left, or right, we see that here in this histogram that the random decision agent has a longer tail in the terms of numbers of blocks measured than the DRL decision agent. So this was also very encouraging because we can use DRL to minimize the number of measurements we have to do and automate it. Finally, we have been looking into fine-tuning, because once we have these features, these particular islands of current, well, we need them to look in a particular way in order to be able to encode a qubit. And this is a simulation of how they should look like. But this is what we actually see every time we find them. A blob with some lines. For those that are experts in transport, you can see this tunneling line coming here, which is not good at all. So what we have to do is start, tweaking all the voltages again in order to arrive at a very good and sharp pair of triangles. So we've done an algorithm that has been able to manage that automatically. We can see how the bias triangles get sharper and more defined with our algorithm. So again, I can tell you just roughly how it works, and I'll be happy to take questions. But the idea here is that we didn't even, this is very difficult again to parameterize, because we don't know, as an experimentalist, we have a feeling of what good bias triangles look like, but it's very hard to actually make a set of rules to say, well, my bias triangles should look this way or another. So the way we did it was to encode these images in a higher level of representation, let's say a latent space. And we have done so for some example bias triangles, and we have chosen targets, bias triangles that we believe as experimentalists that are very pretty and that are very promising. So those we chose as targets. And then when we have a new example, when we have a new image coming in, what we can do is measure the distance in this latent space to these targets. And if this example is very close, it means that there are many properties in this image that are similar to the target, and therefore it might be that it's a promising pair of bias triangles. And if it's too far away, if this latent space it's actually well ordered, then we see that it will be far away. So in that way, we can create a score. How far am I in latent space from that target measurement? And according to that score, I can change the other gate voltages and see if I get a better score. I take another measurement, then I encode it again, and we see again this, we get a new score, and we go through iterations of this problem. And in this way, we are able to completely automatically and without human intervention fine-tune these bias triangles, again, faster than we would be able to achieve manually. So in around 30 minutes. So where are we going next? Well, we have made it through from a virgin chip to these very defined features to encode a qubit. We are working now in the qubit optimization in order to go all the way through this process. what we see is actually some of the tools that we have already developed, such as efficient measurement, are becoming again very useful in the optimization of qubits. And this gives us a hint of how broad these algorithms are, and that can be applied not only to quantum chip experiments, but also to other type of experiments and simulations. With that, I'd like to thank my team and my colleagues and collaborators, and well, thank you.
Thank you very much.